Hi, I'm Fernando Pereira from UFMG, and today we shall talk about a family of code optimizations that finds widespread usage in the implementation of virtually any mainstream compiler. These are the so-called Peephole Optimizations. The idea is to traverse the stream of instructions that constitutes a program with a small window, applying optimizations on the instructions within this window. In other words, we fix a number of instructions that we can see at the same time. The window will let us visualize this number of instructions. It will slide over the program, and then we can optimize the instructions in the sequence. For instance, let's assume that we can see groups of two consecutive instructions. If we see a pattern like this load-store pair, then we can optimize it away. The thing is that the sequence is not really changing the state of memory. And mind it that it could actually happen in practice, even though it looks naive. Sometimes we have this kind of sequences due to the way that register location is implemented, for instance. So the register locator trusts the Peephole optimizer to eliminate some bad code away. Also, Peephole optimizers can improve branches. For instance, the code on the left is equivalent to the code on the right. And the code on the right is a bit shorter, and we can assume that it will run faster. Indeed, concerning jumps, there are many optimizations that we can perform. For instance, how could we optimize this kind of pattern on the left? We could rewrite it to look like the code on the right. The number of instructions is the same, but the code on the right is likely to be faster, for each branch jumps only once. And by the way, could we remove the instruction at L1? Well, if we know that there is no jump going to L1, then yes, we could remove it. Notice that this requirement amounts to checking if L1 is preceded by an unconditional jump. But notice that to eliminate L1, we would require some whole program optimization. At least the knowledge of branches in the entire program. We can gather this kind of information before traversing the program with the sliding window, if this needs to be implemented. Notice that here we are talking about fall-throughs. Have you ever heard this expression before? A fall-through is the basic block that follows a not taken jump. In other words, if the branch is not taken, then the execution flow continues on the fall-through. Let's continue with branch optimizations. Take a look into the sequence in the red box. Can you think about how to optimize it? If you want, as an exercise, you can stop the video and think about it. Well, nothing really new at this point. We can replace the jump to L1 to a jump to L2. That works even in conditional branches. Now take a look into another jump optimization. Do you know when it's safe to carry it out? When is it safe to rewrite the code on the left into the code on the right? Maybe you could stop the video again and then think about it, about those requirements for safety. We had seen before the conditions to perform this kind of optimization. Let me write them explicitly here. So, to move the conditional branch up the instruction stream, we need to make sure that there is no other branch in the program that might jump onto L1. And in this case, that includes the fall-through. So L1 must be preceded by an unconditional go-to. Perhaps you could think a bit on why these conditions are really necessary. But in addition to jumps, there is a very well-known class of optimizations that fit into the framework of Peephole optimizations. They are called strength reductions. Strength reduction consists in replacing some sequences of operations with operations of equivalent semantics, but that are cheaper to be implemented in a particular hardware. In other words, we're removing the weight of some sequences, making them lighter given a particular hardware. For instance, we can replace multiplications by powers of 2 with shift to the left. In many computer architectures, the shift is cheaper to perform at the hardware level than a multiplication. And we can explore machine idioms to implement even more extensive forms of strength reduction. For instance, in the x86 architecture, we have inc, which is an instruction that adds 1 to a register. We can use it to replace simple additions whenever we know that one of the operands is the constant 1. Of course, there are many more machine idioms that we could explore. That was just an example. In the next class, we shall talk about another kind of local optimization. That's called local register location.